Hello guys, how are you? This is Mubin, your physics teacher. So we were discussing about dynamics, and the previous lecture we have discussed what is momentum, what is impulse, what is relation between force and momentum. Further, we are here for the most important topic, that is law of conservation of momentum. Okay. This is the most important topic in dynamics because most of the questions in dynamics comes from here. So, before entering to law of conservation of momentum, we are to learn what is a isolated system. Isolated system. So, the system with no external force is called isolated system. The system with no external force is called isolated system. Okay. The question is there any isolated system possible? No. There is no isolated system in the universe. How? Okay, let me tell you. See, if there are two balls striking to each other, there is a force that is called weight. If they strike to each other, there is a force called friction. Okay, so the external forces present, this is not an isolated system. Yes, we can consider that in gas molecules, the atoms are too much small, so their weight is negotiable. But the thing is, they have uh, intermolecular forces. What? Intermolecular forces. So there is no isolated system present. But the thing is, we ourselves assume that if there is an isolated system, the law of conservation of momentum states that the momentum of an isolated system is always conserved. What does it mean? Conserve. What does it mean? Okay, let me surprise it to you. Let's go back, man. Yes. So consider this ball striking to another ball. Okay. Let's suppose it has mass 1 and it has mass 2. It has velocity v1i and it has velocity v2i. What does it v1i means? It means initial velocity of first body. Initial velocity of body 1. What does V2I means? Initial velocity of body 2. Is it okay? So, when they strike to each other, they exert force on each other. And according to Newton, these forces are always equal. Are you getting me? So, with these forces, uh, they change their velocities. Of course, mass cannot be changed. So, the velocity of first body becomes v1f, and the velocity of the second body becomes v2f. Talking about the initial momentum, what was the initial momentum? Momentum of first body, that is m1 v1, and the momentum of second body, that is m2 v2, and the final momentum is m1 v1f plus m2 v2f. Are you getting me? So this is the equation. So this is the equation. Mark it. The total momentum is always conserved. Are you getting me? Okay. So the simple equation is total initial momentum is equal to total final momentum. Okay. So if there are three bodies, what would be the equation? M1 V1F plus, sorry, my mistake, it is V1I, M2 V2I plus M3 V3I plus M4 V4I and so on is equal to M1 V1F plus M2 V2F plus M3 V3F and so on. Are you getting me? Here is some trick. Now consider this. I have said that total initial and total final is equal. I didn't have said the velocities are constant. Are you getting me? Consider this. There is a ball of mass 1 coming with velocity of 5 meter per second. Consider it. It strikes with another ball of 5 meter per second with M2. Okay. When they strike to each other, they bounce back with the same velocity. Okay. Now tell me, tell me, what is the initial momentum? Isn't it zero? Because m1 v1 plus m2 v2 is equal to m1 5 minus m2 5, because this is minus velocity. Are you getting me? So taking this, if the masses are equal, it will be cancelled. And in this case, we know that this velocity is positive and this velocity is negative. So what would be the total momentum? It would be zero. The total momentum is always conserved. Are you seeing this? The total momentum is always conserved. Okay, let me give you some other examples as well. Consider this now. We have a ball at rest. Yes, I know my drawing is so wonderful. Thank you. So this is a bullet. Initially, the bullet and the gun are at rest. Okay. Initially, the bullet and the gun are at rest. So total initial momentum is zero. It means that when the gun fires, the total momentum must be zero in order to conserve the momentum. And this happens too. If the bullet moves forward, the gun moves backward to conserve the law of conservation of momentum. Okay, let's say the gun is of 2 kgs and the bullet is of, I think, 200 grams are more than enough. So it would be approximately 0.2 kg. Okay, I hope I'm not delivering the lecture very fast. So if the velocity of the bullet is 300 meter per second, what would be the velocity of the gun? We know that the initial and the final momentum is conserved. If the initial is zero, we can state that uh, m1. We can say this as well. Okay, let me write the first equation. M1 given I plus m2 v2I is equal to m1 v1f plus m2 v2f. Consider this. What would be the value of initial momentum? It would be zero, isn't it? Now, what is m1? It is 2 kg. What is v1f? We don't know. What is m2? What is m2? It is 0.2 kg. What is v2? It is 300 meter per second. So, taking it to the other side, it would be approximately equal to minus 60 2 v1f and taking to this side v1f would be equal to minus 30. So you have noticed that the velocity of the gun was not equal to the velocity of the bullet, but the total momentum of the bullet and the gun was equal. Are you getting me? Let me give you some other examples as well. If we are talking about a rocket, a space shuttle, okay? If we talk about a space shuttle, they have compartments that are filled with fuel. If when they consume one apartment's fuel, they throw it down. Okay, they throw it down. By this, their velocity increases because the mass decreases and the velocity goes up. Are you getting me? Okay. Let me give you some other example. Let me do it numerical as well. Consider this. Suppose that a space shuttle was having a mass of 300 kgs with two parts. Each part is 150 kg. Each part is 150 kg. So when it was combined, they were moving with a velocity of consider 9,000 meter per second. Okay, they were moving with 9,000 meters per second. What was the initial momentum? Initial momentum would be equal to 300 plus 9,000 multiply. It would give us this much amount. Okay. So I am saying that if this falls, it consumes the fuel and make it fall. This compartment's velocity becomes 7,000, sorry, 8,000 meter per second, and its velocity becomes 10,000 meters per second. Is the momentum conserved now? Let us check. Okay, final momentum would be m1 v1f plus m2 v2f. Okay, so m1 is 150 kg, v1f is 10,000 plus m2 is 150 kg. Sorry, 150 kg, and the velocity is 8,000. Checking it, 1500 multiplied by 8, it would be equal to 1515, that is 30. 30 times 4, it would be 1200, 1234. Now, summing it would be equal to 2, 7, 1, 2, 3, 4, 5. Isn't the law of conservation of momentum followed by them? See, see the answer. Okay, are you getting me? Okay, let's go, guys. I will meet you in another video. Sorry. Hello, guys. Hope you are doing well. So we were doing what we were doing. We were doing some past papers on uh, Hello guys. So we are doing some past papers. Okay. Read this question. Read this question carefully. A ball has a mass m. It dropped into the horizontal plane with this velocity. So just as the ball makes contact with the plate, it has a velocity v, the momentum g, and the kinetic energy e. For those who don't know kinetic energy is equal to half mv square. Okay. We are not going to discuss it in long terms because this is an entirely new topic. Okay. So write down an expression for the momentum E that to mass and velocity. So what would be the mass of, and velocity of this? K is equal to mv, isn't it? Okay. Hence, the it shows that the kinetic energy is given by this expression. Okay. Let's prove this. Uh, Kinetic energy is equal to half mv square. If we divide mass and multiply the mass as well, why we are doing this? Because we are to prove that E is equal to E square upon 2m. Okay, so m square v square, isn't it equal to mv whole square upon 2m? Okay, so this is mv is equal to momentum, and this would be equal to mv square. Mv square would be equal to e square upon 2. Are you getting this? So, he is saying that there is a spring. He is saying there is a spring. Okay, there is a small trolley of mass 0.8 kg and a big trolley of mass 2.4 kg. When the thread is cut, they will both move in opposite directions. Okay, so if they do both move in opposite direction, what is the ratio of their velocities? What is the ratio of their velocities? Okay. Uh, Let us do some suppositions as well. The velocity of small trolley is small v, and the velocity of big trolley is capital V. Okay. According to law of conservation of momentum, we know that the both momentums would be equal because the initial momentum was zero. So both momentums are equal and opposite in direction. So we can say that mv must be equal to capital M v. Okay. So what is the value of small m? It is 0.8. What is the value of v? We don't know exactly. What is the value of capital M? It is 2.4. What is the value of capital V? We don't know. Okay. He asked us the ratio of small v upon capital V because the small mass has smaller velocity. So we divide capital V here and small v here. It would be 2.4 upon 0.8, that is equal to 3. Hence proved. Are you getting me? In the next question, he is saying, use the answer in 1A2 and B1 to calculate the speed of the trolley of mass uh, 800 gram. Okay, okay, this part cannot be calculated right now because we are to do kinetic energy, and I didn't solve the part of kinetic energy. It was not related to us. Okay, so it is the second. Second question, a ball B of mass 1.2 kg traveling at a constant velocity collides with a head on with a stationary ball S of mass 3.6 kg. Here's a mass of 1.2 kg ball. Here's a mass of 3.6 kg. It is stationary, so V2 would be 0. This velocity is unknown, I think. The variation with time t of the velocity v of the ball during uh, and after collision with the ball is shown in figure this. So, state the significance of the positive and negative velocity v. He say what is the significance of positive velocity and then negative velocity. Okay. So the thing is, if this ball is coming towards this, okay, so when it strikes the ball, it will move in opposite direction. Yes, it is possible. Okay, because we are to conserve law of conservation of momentum. If it was moving in this direction, was moving in this direction. After collision, if the velocity is negative, then the big ball must move towards this direction. So the momentum would be conserved. Are you getting me? We can write over here the larger mass will move. So to keep law of conservation of momentum conserved, small ball reverses. Small ball, small ball reverses. Okay, so moving forward, use figure 2.2 to determine for ball B during the collision with the ball S the change in momentum of the ball B. We are to calculate the change in momentum of the ball B. I think it would be the ball B. What would be the change in momentum? Okay, so we can easily use this equation m1 v1 I plus m2 v2 I is equal to m1 v1 f plus m2 v2 f. The initial momentum of the second ball, we can say that the ball B was 0. Ball 1 had a mass of 1.2 kg and initial velocity of 4 kg. Okay, 4 meter per second. My mistake. So it was having 1.2 kg mass and 4 meter per second of velocity. What was the final velocity of the ball? It was 1.2. It was, I think, you can see in this uh, chapter, it is about 0.8 minus 0.8. Okay, so minus 0.8 plus m2. What is the value of m2? It is 3.6 kg, but we do not know about V2F. You can calculate it as well. It would be 4.8 minus, let me have a calculator with me. It is 0.96 plus 3.6 V2F. Rearranging it in making V2F as a subject, we would get 4.8 plus 9.6 upon 3.6. Okay, the answer is 1.6. The answer is 1.6 Newton seconds. Okay, so we are ending the video of questions of momentum. and we will have some 2D momentum questions as well.